Hi, folks. Today we're going to talk about techniques of proofs. And so when we think about math, everything that matters is all about the proof. And so in science, scientists use evidence and experimentation to demonstrate whether an idea is plausible. In mathematics, evidence and experimentation are not enough. We seek to demonstrate that something is true no matter what. And this demonstration is called a proof. And so a proof takes a conjecture or statement and determines if it is true or not using a series of philosophically true statements. To prove something, you need well-defined objects, things which have a clear definition. Using the definitions and known or provable properties, a proof will connect the ideas in the statement in a verifiably true way. If given, we get a theorem. Now, there is some fine detail work here. When we're talking about proofs, we're going to be talking about the structures where we can essentially begin with one statement and have a series of statements which we can prove are true and lead to a conclusion. There are other strategies, but there's also a hidden layer in there based on what does it mean to be true or false. We will talk about that later on in this lecture series when we discuss what is it called? Logic. Because symbolic logic really is the underpinning of all of this proof stuff that we're going to be dealing with. That said, before we start, let's make sure we have some key terms. Our first one is a conjecture. And so a conjecture is a statement which hasn't been proven or disproven yet. One example is the Collatz conjecture, which has not been proven or disproven yet. A theorem is a statement which has been proven. A lemma is a smaller theorem, which is used to prove a bigger theorem. Oftentimes, we call theorems the big ones. And then if we're building up to a big theorem, we will call all of those intermediate steps lemmas. A corollary is a smaller theorem which usually comes as a natural result of the bigger theorem. And so if we have proven something really big and then there's some tiny piece of it, well, sometimes that tiny piece we'll call a corollary. A proven statement, oftentimes if something really tiny is proved, we'll just call it a proven statement. We won't even give it some fancy name. And then a property, given a structure, it's a descriptive, provable characteristic of the structure. For instance, the commutative property or the properties of equality or exponential properties. All of those are properties which we can prove, and once we've proven them, we can use them to do other things. For instance, the distributive property. It's a property which we know and understand, and so when we need to, we can use it. Finally, we have an axiom or a postulate. An axiom or a postulate is a statement which is accepted without a need for proof. Note, when we say that it's accepted without need for proof, it's more like this is the characteristics of whatever system we're dealing with, and we may later consider what happens if one of the axioms is not true. For example, when we think of geometry, geometry is described by 5 axioms. All it takes is 5 and you get the entirety of geometry. Well, one of them is called the parallel postulate. And if we have the parallel postulate in play, we get our standard Euclidean geometry. If we say we don't want to deal with the parallel postulate, then we get hyperbolic geometry, which is kind of like the geometry on the surface of a globe. And so we often ask what happens when we don't have these axioms, but generally we have a set of axioms that we play with. There are a number of techniques to prove things. Let's discuss the fundamentals. Our first one is going to be the direct proof. A direct proof is a style of proof which connects your premise to your conclusion by connecting a series of true statements. This is one of the most standard forms. You start at point A, you get to point B, and you try and get there as quickly as you can. When asked to prove a statement, use the definitions and known or previously proven relationships to create a series of statements. All of the statements need to be true, and they should build upon one another until you reach the last statement, which is the statement you were to prove. Here's an example. And so prove that if P is even and Q is odd, then P plus Q is odd. In this case, we have some things we need to define. Do we know what it means to be even? Do we know what it means to be odd? Do we know what it means to add? I mean, these are all things which we have to be able to define. And so here's our proof. We suppose that P is even and Q is odd. Even means P can be written as 2m for some integer m. Odd means Q can be written as 2n plus 1 for some value n, where again, m and n are both integers. The expression P plus Q can then be written as 2m plus 2n plus 1. Using the distributive property, we can factor that 2 out, which means we can rewrite this as 2 times m plus n plus 1. Well, if we let k be equal to m plus n, then P plus Q is equal to 2k plus 1, and k is an integer. This is the definition of odd. Thus, it's been proven. P plus Q is equal to an odd number, provided that P is even and Q is odd. That is a direct proof. You start with the base definitions and you just work your way straight through it. Here's another example. If you'd like, pause the video and give this one a shot. So we are going to prove that for any n greater than 1, it holds that n cubed plus 1 will be a composite number. The nice thing about n cubed plus 1 is it's factorable. We can factor this using algebra. And so by the sum of cubes formula, we can factor n cubed plus 1 as n plus 1 times n squared minus n plus 1. Well, if we're saying that n has to be greater than 1, we can show that the first factor is strictly greater than 2. And so if n is greater than 1, then 1 plus 1 is greater than 2. We can similarly show that the second factor is strictly greater than 1. And so looking at the second factor, n squared minus n plus 1, well, if we replace all of the n's with 1's, we're going to get 1 times 1 minus 1 plus 1. Well, that's 1. So that means that this term is also greater than 1. Since n cubed plus 1 has 2 factors, both greater than 1, it is a composite number. There we go. Again, very much a direct proof. We start with the base definitions, we use whatever properties we have, and we get ourselves to an answer. Here's one more. Prove that 0.9 with a bar over it is equal to 1. If you'd like, pause the video and give it a shot. There are actually many different proofs for this one. This will be one of them, and this is probably the easiest one to recognize. The decimal form of 0.9 bar has a repeating decimal, 0.999999999, so on. As such, it is a rational number. We know of other numbers with this repeating pattern. In particular, 1/3 is equal to 0.3333333333 is equal to 0.3 bar. Multiplying each side of this equation, the 1/3 is equal to the 0.33333, we get 3/3 is equal to 0.9999999, which is equal to 0.9 bar. But 3/3 is 1. And so it's been shown that 1 is equal to 0.9 with a bar over it. This one's a fun one because it emphasizes the idea that when we're talking about two numbers, there's always going to be some number between any two numbers. And if there isn't any number between two numbers, then those numbers must be the same number. In this case, it might not be obvious that these two numbers are the same number, but their difference is 0. And so if their difference is 0, that means that they are the same number. A second approach to proving things is to use a counterexample. And so in math, if something works 100 times or 1,000,000 times or as many times as you like, one could say that there is evidence to support the claim, but not in math. In math, until there is a formal proof connecting the dots, the idea remains a conjecture. All it takes is one counterexample to disprove a statement. When asked if something is true, always consider the possibility of a counterexample. And the counterexample might be so far off that it's not even plausible to see that number in the real world. But we're not talking about the real world, we're talking about math. And so abstract concepts pop up a lot. Here's our first one. Prove or disprove that all prime numbers are odd. Well, this one is very easy to disprove. 2. The number 2 is a prime number and is not odd. It's only divisible by 1 in itself, so it is prime, and 2 is extremely even. Thus, we have shown that not all prime numbers are odd. That's all it takes for a counterexample. Just one example, and we've disproved it. Here's another one. Prove or disprove that for all x greater than 1, it holds that the natural log of the natural log of x is less than e to the e. And if it helps, I've graphed it out here. We can see this. This appears to be an logarithmic scale. And so we have e to the e, which is up here. And then we have natural log of x. And up to this point, we are at a 1 with 100 zeros after it. At this point, we are talking about number of atoms in the universe. That is how large this number is. And we are being asked to prove that for all x greater than 1, this thing holds true. Well, it certainly looks true, but we're talking about math, and there are numbers larger than a 1 with 100 zeros after it. And here's our proof. So let x be anything greater than or equal to e to the e to the e to the e. Then the natural log of the natural log of e to the e to the e to the e is greater than or equal to e to the e. Thus, the statement has been disproven. Note, if you were using a calculator to find this counterexample, you would probably have a very, very hard time. This number that we found, e to the e to the e to the e, it's 2.33 times, let's see, this is a 1 with 1,656,520 zeros after it. That is a very, very, very large number. But all we need is one example, and there it is. And so this is not true. Natural log of x is not always less than e to the e. The next one's a little bit different. And so our next style of proof is a proof by contradiction. I'll be honest, I use these more than just about any of the other proof types. And so a proof by contradiction is a style of proof which works like a double negative. Whatever we are trying to prove, we assume it is false and then try to prove that. Playing around with it, eventually we reach a contradiction on our initial assumption, which means that we assumed something false. And, well, if we didn't assume it to be false, then it must be true. It's kind of like saying, oh, you're saying this thing is true? Well, what if it's false? What's going to happen? And if your false thing ends up leading to a contradiction, then that tells us that it must have been true all along. And so let's try one. Prove that all prime numbers greater than 2 are odd. And so I'll give you a shot if you want. Take a chance at it. I will show you the answer. Proof. Suppose that n is a prime number greater than 2 and is even. And so we're saying, instead of thinking that it's going to be odd, let's suppose it's even. What could happen? Then n has exactly 2 divisors and is only divisible by 1 and itself. And so that's what it means for this number n to be prime. Then n can be written as 2k for some natural number k. Well, that's what it means for the number to be even. Since n is greater than 2, k must be an integer greater than 1. Because 2 times k is equal to n, which is greater than 2, so k must be more than 1. But that's where we start to get ourselves in trouble. Because that means that n can be written as the product of 2 numbers, 2 and k, neither of which is 1. 2 is necessarily a divisor, meaning that n has more than 2 divisors. Well, that's a contradiction. We said that the number was prime, and we just proved that if it's even, it's not prime. And so this is a contradiction, meaning if n is a prime number greater than 2, it cannot be even and is therefore an odd number. That's a proof by contradiction. Here's another one. Prove that the square root of 2 is irrational. This is one which is credited to Pythagoras, and so this is a good one. If you'd like, give it a shot. All right, let's go through it. And so here's the proof. We're going to prove this by contradiction, which means we're going to start with the idea that the square root of 2 is actually rational. And so if square root of 2 is rational, that means it can be written as the form p over q, where p and q are natural numbers and they have no common factors. Well, if we square both sides, that would mean that 2 is equal to p squared over q squared. Cross multiplying, we get 2q squared is equal to p squared. This tells us that 2 must be a divisor of p squared, because this is how we defined divisors. And so by extension, 2 must be a divisor of p. And so since 2 is a divisor of p squared, 2 has to also divide p. This means that p is equal to 2k for some natural number k. Well, if we evaluate, we could then say that 2q squared is equal to 2k squared. We can clean this up. This would give us a 4k squared, and then dividing both sides by 2, we get q squared is equal to 2k squared. This means that 2 is a divisor for q squared, much like it was a divisor for p squared. Well, if 2 is a divisor of both p and q, we've reached a contradiction. Because in our defining this rational thing, or a rational number, we said that p and q have to have no common factors. To be a reduced fraction, they can't have anything in common. And so we've reached a contradiction. Thus, the square root of 2 is not rational, which means it must be irrational. Thus, it is proven. One more example. Prove that there are an infinite number of prime numbers. For this one, we're going to construct a new number. And so suppose that there are finite number of prime numbers, and let m be the number of prime numbers. We're going to create a new number p, which is formed by taking all of the prime numbers and multiplying them together and adding 1. And so we know that there are m prime numbers, or at least that's what we're assuming if there's a finite number. And so p1 times p2 times p3 all the way multiplied by p sub m, our mth p value, our mth prime. And then we're going to add 1 to that. Well, if we divide p by any prime number, there will always be a remainder of 1. And so looking at this, if we divided this thing by p sub 1, we would be left with 1. If we divide by p sub 2, we're left with 1. If we divide by any of these primes, we're always going to have a remainder of 1. Since p is not divisible by any prime number less than itself, p is only divisible by 1 and itself, meaning this new number we created is prime. But we said that we already had all the primes. And so in this case, there must be m plus 1 prime numbers when we said there's only m. That's a contradiction. We contradicted ourselves, which means that there's not going to be a finite number of prime numbers. In fact, there must be an infinite number of prime numbers. One last thing to be cautious of, and that is when you are doing a proof, you have to make sure that everything follows. If you have something where there's some gap in logic, you might end up getting yourself in trouble. And here is a common example. Prove that 1 is equal to 2. And here's the standard proof that 1 is actually equal to 2. We start by saying, let's let a be equal to b. Then we multiply both sides by a, which gives us a squared equals ab. We can then subtract b squared on both sides, and then we can factor. Once we've factored, we'll note that both sides have an a minus b. And so we can divide both sides by a minus b. And from there, we get that through substitution, a and b are the same thing because we said a is equal to b. So that means 2b is equal to b. Dividing by b, we get 2 is equal to 1. Now, you may not be aware of this, but 2 is in fact not equal to 1. And so something went horribly wrong. The question is, where did we make our mistake? And the answer is we divided by 0. And so when we were talking about our divisibility property, we have to be careful that we don't divide by 0. Since a is equal to b, a minus b is 0. And so a plus b times a minus b, if we divide that by a minus b, we're really dividing everything by 0, which is not allowed. And so that's how we broke math. And in breaking math, we proved that 2 is equal to 1. Don't do that. Our final thought on proofs. When it comes to mathematics, proof is what matters. We can say statements, but math is all about determining when something is certain or not. And to reach certainty, we need to be able to prove that something is always correct or adjust the statement to better represent the truth of the situation. This set of lessons, we focused on numbers because that's something which we're familiar with. Going forward, we're going to be exploring much more abstract structures. And in order to prove things in these abstract structures, we need to be able to understand what a proof is and what our ultimate goal is. Hopefully this brief introduction has helped with that a little bit. With that, I'll let you get to work exploring where you find proofs in a real world situation. Good luck, folks.